I'm going to talk about pseudorandom function-like states, and I'll present new definitions of this object and also some constructions. Um, and this is joint work with Aditya Gulati, Luowen Qian, and Yuen. So what are pseudorandom quantum states? These are states that are efficiently computable that look like Haar-random states. Let's try to formalize this. So the first property is that we require from a PRS notion is the efficient generation property, which states that there exists a polynomial-sized quantum circuit that takes as input a lambda bit string k, and it outputs an n-qubit state. For simplicity, let's just consider the case when the output is a pure state. Most of the discussions will generalize to the case when the output of a PRS is a mixed state. We use the notation n output PRS or n PRS to denote a PRS scheme where the output length is n. The second property we require is the pseudorandomness property. In the simplest case, what we require is that the output of a pseudorandom state generator on a randomly chosen key should be computationally indistinguishable from a Haar-random state on n qubits. So this is sort of the simplest case, but in many cases, this sort of notion does not suffice. So we consider like a Q copy version, which states that even if I give you Q copies of a PRS state, this should be computationally indistinguishable from Q copies of a Haar-random state. And moreover, the adversary can choose this Q, this polynomial Q. So it's important that we let the adversary choose the polynomial Q, I mean the number of copies he requires. If you sort of fix Q ahead of time, then this gives us a weaker notion called Q state design. So that is sort of like well studied in the quantum information theory literature. So what do we know about PRS? So in terms of constructions, we know how to construct PRS from one-way functions. This was first discovered by G. Liu and Song and subsequently improved by a couple of works by Brzezinski and Shmueli. There's something that is sort of not clear from these works, which is that it's not even clear that one-way functions is necessary to construct PRS. Right, and so this gives us sort of like the first question that we're going to tackle, which is to understand for what parameters does for what output lengths of PRS does information theoretic PRS exist. So I should clarify what I mean by information theoretic PRS. What I mean is that the PRS is said to be information theoretically secure, even if like computationally unbounded adversary cannot distinguish Q copies of a PRS state versus Q copies of a Haar-random state. Okay, so this is something that's still not clear that we are going to tackle. So what else do we know about PRS? In terms of applications, what we know is that it has applications in quantum gravity and also quantum machine learning. Okay, so for many applications, it turns out that PRS is not very sufficient, or it's not the right tool to use. So to come up with a better notion, we introduced the notion of like pseudorandom function-like states in a previous work with Luowen and Henry. So what is this pseudorandom function-like states? If you're familiar with classical pseudorandom functions, this is going to be like a quantum analog of pseudorandom functions. Just like a PRS scheme, we require PRFS to satisfy two properties. The first is the efficient generation property. This states that there exists a quantum polynomial time algorithm that takes as input a string k as before, a lambda bit string k as before, and additionally it also takes as input a d bit string x, and it outputs a state psi x. Okay, so we denote a PRFS to be ND output PRFS or ND PRFS if the input length is d and the output length is n. Okay, and in terms of security, what we require is that even if I give you Q copies of Q PRFS states evaluated on Q inputs, then they should be computationally indistinguishable from q copies of independently chosen Haar-random states, q Haar-random states. Okay. So in some sense, I'm using the same q to denote the number of inputs and also the number of copies. I mean, this is not necessary. This is just done for simplicity. So informally, what is this saying? What this is saying is that unlike a PRS, where you use the key to only generate one PRS state or one pseudorandom state, a PRFS allows you to use the same key k to generate multiple PRFS states. Right. So in this particular case, you can generate 2 to the d pseudorandom states. Right. Okay. So one thing I want to point out about the security definition considered in the previous work is that is the selective aspect of it, which is that somehow all the inputs x1 through xq need to be declared ahead of time, and then we give the evaluations of the PRFS on these inputs to the adversary. Right. So in some sense, we don't let the adversary choose these inputs adaptively. Okay, and it turns out that selective security is not useful to capture many applications. So for example, in the previous work by QY, we could only show that selectively secure PRFS implies selectively secure private key encryption. But instead, if you wanted adaptively secure private key encryption, then this notion does not suffice, which means that we should look for stronger security notions. This is the second question we're going to tackle. Okay, so finally, in the previous work, they showed that many applications of one-way functions can actually be constructed from just using pseudorandom quantum states. For example, encryption, signatures, commitments, randomized encodings. This is great because of a result by Kretschmer, who shows that pseudorandom quantum states can be a weaker assumption than one-way functions. On the other hand, there is still something nice about constructions of these primitives from one-way functions, which is that if you look at the communication required by these constructions from one-way functions, they only need to be classical, whereas the applications from PRS requires quantum communication, right? And in many scenarios, classical communication is more desirable, right? So this gives us to a natural question whether we can construct commitments and encryption from PRFS with only classical communication. Right? I think this is the final question we're going to tackle. So just to summarize the questions, the first question is, when does information theoretic PRS exist? Second is to look for stronger security notions for PRFS. And finally, we want to construct cryptographic applications from PRFS just using classical communication. So here are our results. So let's address the first question. And what do we show? We show that as long as the output length is larger than logarithmic in the security parameter, then we need computational assumptions. So this is in some sense tight because of a previous work by Brzezinski and Shmueli, who showed that if the output length is some constant times logarithmic in the security parameter, for some constant, then information theoretic PRS does exist. So of course this constant is some constant less than 1. So in some sense this makes our result tight. On a side note, we also come up with a different construction of PRFS from one-way functions. I mean, the construction is the same as what was considered in JLS and Brzezinski and Shmueli, except that our proof is significantly simpler. Okay, so let's address the first question. The second question is to look for stronger security notions. So we come up with a new definition of security called adaptive security. So here's the security notion. So we allow the adversary to choose the inputs adaptively, meaning that the adversary can query x1, get a PRFS state, get q copies of the PRFS evaluation on x1, and then adaptively can decide what the next input has to be, right? And then it can query x2, and then so on. So moreover, we also consider a stronger security guarantee, even stronger security guarantee, where we can allow the adversary to make superposition queries, right? So the adversary can query make superposition queries to the oracle, where you query on like superposition over all possible inputs, and it can receive the evaluation of PRFS on all possible inputs in superposition. Okay. And we come up with a stronger result where we show that even adaptive PRFS can be constructed from post-quantum one-way functions. Okay. So that addresses the second question. Third question is to understand whether we can construct these primitives with only classical communication. And we show that you can actually construct many of these interesting primitives like encryption, commitments, and randomized encodings with just classical communication. So we don't construct signatures, so coming up with signatures from PRS with only classical communication is still an interesting problem. Okay, so in more detail, we show that we can construct bit commitments from PRFS with classical communication. And we also come up with the construction of pseudo one-time encryption from PRFS with classical communication. Okay, so in this talk, I'm only going to focus on addressing question 1 and question 3. If you are more interested, you can look at the full version of our paper for techniques regarding addressing question 2. So let's start with the first part, which is to understand when does PRS require computational assumptions. Okay. So here is our formal theorem statement. We show that as long as the output length is larger than logarithmic insecurity parameter, then there exists some adversary. This can be computationally unbounded, such that for some t, the computationally unbounded adversary A can distinguish whether it is given t copies of PRS state versus t copies of a Haar-random state. Okay. And this holds for any secure PRS generator G. Moreover, like the distinguishing probability is at least 1/3. Okay, so let's see how to prove this statement. We are going to make an observation, which is that with overwhelming probability, the output of a PRS is going to be an almost pure state. So what is an almost pure state? It just means that if you look at there exists a pure state such that the trace distance between this pure state and the output of the PRS state is going to be very, very small. Okay? And this holds with the overwhelming probability. Okay. So why is this true? This is simple proof by contradiction, which is that let's say the distinguisher is given 2 copies of this state, then it can tell apart whether it's getting a state from a PRS or whether it is getting a Haar-random state. Right? And here is what the distinguisher is going to do. It's going to perform a swap test, and it's going to output 1 if the test succeeds. So if it is a Haar-random state, then it's a pure state. So the swap test is always going to succeed. So the distinguisher will always output 1. Okay. So if it is a PRS state, you can show that the distinguisher outputs 1 with probability at most 1 minus 1 over Pauling. So it's bounded away from 1. Right. So and thus the distinguishing probability is non-negligible, which would violate the pseudorandomness of G. Okay, so for the rest of the proof, I'm just going to make a simplifying assumption that the output is always pure. This just makes things simple, and moreover, the arguments can be generalized to the case when it's almost pure. Okay, so let's look at the space spanned by all the t-copy PRS states. And let's look at the dimension of this. I claim that the dimension of this subspace is at most 2 to the lambda. Why is this? This is because there are only 2 to the lambda possible keys k. Right? And thus the dimension can be at most 2 to the lambda. On the other hand, if you look at the dimension of the subspace spanned by t-copy and qubit Haar-random states, it is given by this binomial expression 2 to the n plus t minus 1 choose t. And this follows from known facts in quantum information theory, because T-copy n-qubit Haar-random states generate a subspace called the symmetric subspace, and the dimension of the symmetric subspace is given by this expression. Okay, so this is interesting, right? Because if you look at the space spanned by T-copy PRS states, the dimension does not increase no matter what T is. It's always going to be upper bounded by 2 to the lambda. Whereas if you look at the T-copy n-qubit Haar-random states, if you keep increasing T, the dimension of the space keeps increasing as well. So in order to create a gap between these two dimensions, I just have to pick T appropriately. So if I pick T to be lambda plus 1, then we can show that the dimension of the subspace spanned by T-copy PRS states is going to be at least 6 times 2 to the lambda. Okay. Whereas this is going to be at most 2 to the lambda. So what I did so far is to sort of create a gap between the dimension of the two subspaces. So using this, I'm going to create the following distinguisher. So the distinguisher that distinguishes T-copy PRS states versus T-copy Haar-random states as the following. It's going to, given T copies of the state, it's going to measure with respect to, it's going to measure the state with respect to the following projective measurement, where we define the projector as follows. This projector is going to project onto the subspace spanned by all the T-copy PRS states. Okay. So note that if the distinguisher is given T copies of the PRS state, then the projector is going to succeed with probability 1. Whereas if the distinguisher is given T copies of the Haar-random state, then it's going to distinguish with probability at most 1/6. So thus there is a gap between the probability that the distinguisher outputs 1 when given PRS versus Haar-random. Thus we were able to violate the pseudorandomness property. Okay, so this concludes the first part. So let me move on to bit commitments. We'll see how to construct bit commitments with classical communication from PRS. Okay, so bit commitment is a two-party protocol between two parties. Let me denote them by Alice and Bob. Alice is a bit X, and it interacts with Bob in two phases. The first is the commit phase, and the second is the opening phase. So in the commit phase, Alice is going to commit to its message X. You can think of Alice as putting its message in a log box and sending it to Bob. And in the opening phase, Alice reveals X and also whatever randomness it used in the commit phase. Can think of this as revealing the key and also, revealing the message written on some paper to Bob. So what Bob does is it uses the key to open the logbox, check if the message inside this box is the same as the message Alice wrote on the piece of paper, and if so, it outputs accept, otherwise it outputs reject. Okay, so we require a commitment scheme to satisfy two properties. So one is the hiding, the other one is the binding. So hiding property just says that if Bob is evil, then you should not be able to distinguish whether Alice is committed to bit 0 or bit 1. Binding property is a bit more tricky to formalize in the quantum setting. In the classical setting, we roughly require that if Alice is evil, then it should not be able to open to a different message than what was committed to in the commit phase. Right, and this definition turns out to be sort of impossible to achieve in the quantum setting, and the reason is because of what is referred to as a superposition attack, where Alice need not commit to anything in the commit phase. It can send like superposition over commitments to 0 and 1 in the commit phase, and in the opening phase it can sort of measure this and depending on what the measurement outcome is, it can open to either bit 0 or bit 1. So it's sort of like delaying what bit it committed to the opening phase, which is contrary to what we want from the binding property. So in the quantum setting, the way AQI formalized is using like an extractor-based definition, where after the commit phase, we have a joint state between Alice and Bob, and we apply an inefficient extractor on Bob's state to recover an input x star. And the guarantee that we have from this x star is that the probability that Alice can open to 1 minus x star such that Bob accepts is going to be negligible. right? So it's, in other words, X star sort of uniquely determines the bit Alice can open to in the opening phase. Okay, so we'll see how to construct bit commitments from ND-PRFS. So let me first recall the construction AQ I had. So we don't need to really understand the construction since we are going to sort of improve this construction to just have classical communication later on. But it's good to sort of understand the template. So in this construction, Bob sends a random 2 to the d times n qubit poly to Alice. Alice sort of like picks a PRFS key k uniformly at random. It evaluates the PRFS on all possible inputs. And then it either sends a tensor of all these inputs, of all these PRFS states, sorry, if the bit Alice wants to commit is 0, or it sends the tensor of all these states conjugated with a poly p, which the Bob sent, if the bit Alice wanted to commit was 1. Okay. So one important thing to note is that d is logarithmic, so the communication and also the computation is going to be polynomial time. And in the opening phase, Alice is going to send the PRFS key k and also the input x, and then Bob can check if the state sent by Alice was correct or not using this. Okay, so how do we make this protocol have classical communication? So in order to understand that, note that the only place where the communication needs to be quantum is when Alice sends all the PRFS states to Bob. So how do we make this classical? The idea is to use state tomography. So what Alice is going to do is it's going to run a tomography procedure on 2 to the n copies of the PRFS state to get a classical description of the state. So you might think that n is 2 to the n is bad, but note that n is actually logarithmic, and even d is logarithmic. So you're only running this tomography on like polynomially many copies of the state, and so everything is sort of efficient. And even the number of states that you're running the tomography procedure on is also polynomial, right? Because 2 to the d is also polynomial. So we use the poly-based tomography procedure due to Lowe, who shows that the output of the tomography procedure, the difference of the output of the tomography procedure and the original density matrix, if you take the square of Frobenius norm of this quantity, this is at most 1/3 with overwhelming probability. It turns out that this is not quite what we want. So we want the 1/3 to be negligible in order to prove the correctness of the commitment scheme, and sort of we improve this tomography procedure to replace 1/3 with negligible, and then the correctness of the commitment scheme will follow. So how do we make the communication classical now that we have we have the classical description of the density matrices? So instead of sending the density matrices, we'll just send the classical matrices M1 through M2 to the D. Right? The rest of the scheme is the same as before. And even Bob is going to perform the tomography procedure to check if whatever classical matrix Alice sent in the second message is correct or not. Okay, so this sort of roughly concludes the description of the scheme. So if you want to know more details, again, refer to the full version. So let me summarize. So we show how to construct PRS with omega log output length. The constructions of like PRS with omega log output length requires computational assumptions. We also gave a new definition of security for PRFS that we called adaptive security. One thing I didn't talk about is how to construct adaptively secure PRFS from postmortem one-way functions. And finally, we also saw how to construct commitments from PRFS with classical communication. So the same sort of idea of using tomography to make communication classical can also be used to construct encryption from PRFS with classical communication that I didn't cover. And this sort of concludes this talk. Thanks for listening.